All right, we're going to talk about binomial distributions, also kind of called binomial experiments today. And we're going to start out by just giving an example of a pretty understandable sample problem in binomial distribution. And then we'll go into the details about what a binomial distribution is and how to figure out if the situation you have does work with a binomial distribution. Then we'll learn about how Excel handles binomial calculations and do some examples. All right, so first off, let's talk about what is a binomial experiment. We're going to start with a typical binomial problem, which I've got here at the top of this spreadsheet. If I toss a coin 10 times, what is the probability that I will get exactly 3 heads and 7 tails? I mean, that's certainly possible. We know that the probability on a single toss is 50-50, right? 1/2, 1/2, 0.5, 0.5, however you want to put that. But it is possible when you toss a coin 10 times to get 3 heads and 7 tails. We want to know what the probability of that happening is. So that's kind of a typical binomial problem. Let's talk about what it takes for something to be binomial. The first thing we need to look at is that there needs to be a fixed number of what are called trials. Each repetition is called a trial. So each time you toss the coin, each toss is a trial, and that is a fixed number. So if you are going to toss a coin however many times it takes before you get a heads, that is not binomial because that's not a fixed number of times. It has to be a fixed number. You have to know that number before you start. I'm going to toss this coin 10 times and only 10 times. No matter what my results are, that's how it's going to be. That's what you need to have a binomial experiment. Of course, it could be any number of times. You could toss a coin 87 times if you wanted. As long as it's a fixed number, you're good. The second thing for binomials is that the trials are independent. That means if I toss a coin next time, whatever I've gotten previous to that doesn't matter. And that works with tossing a coin, right? It doesn't matter what you got before. That's not going to affect what you get this time. So you need to watch out for that. The third thing, and the hallmark of binomial is where the by comes from, is that there are only 2 possible outcomes, heads or tails. So if you were tossing a coin and you had some kind of surface that allowed the coin to get stuck in sideways on its edge, that would no longer work for binomial distribution because then you'd have heads, edge, tails, and that's 3 possible outcomes. Has to just be 2. So we have to be careful where we toss our coin to make sure there are only 2 possible outcomes. In general, in statistics, those outcomes are called success or failure. So if we're looking at for the number of heads we get, heads would be considered success. If we were looking for the number of tails, that would be considered success. So we choose what we call success. And sometimes success can be a really bad thing. So if you're studying diseases, success could be someone gets the disease, the rat gets the disease, right? So those words are a little squishy, which is why I put them in quotes. The success really means what are you interested in, and the failure means you didn't get what you want, whether that's a positive thing or not. There's no overlap between the two, and there are no other possible outcomes. Has to be 2 and only 2. And the last thing is the probability of success has to be the same every time. So if you were flipping a coin and you used a fair coin And then you got a loaded coin that where the probability is going to be different because it's made especially to give more heads, then that's no longer binomial. It has to be the same every time. So if you are using a fair coin, you better use a fair coin through everything. And if you're not using a fair coin, then you need to use that coin through everything. And your probability is not going to be 0.5 anymore. You're going to use some other probability. All right, so that's what a binomial experiment is. We have some notation changes. And this now is the number of trials in the experiment. If you're surveying so many people, that is N as well. How many people you survey, each person's answer would be considered a trial. P is the probability of success. And then 1 minus P is the probability of failure. And this is for each trial. So when you're flipping a coin, that's going to be 0.5 for failure and 0.5 for success. Capital X is the number of successes in N trials. And little x is the current trial. So if you're flipping the coin 10 times and you get 3 heads, capital X would be number 3. If you're in the middle of flipping the coin and you're on toss 5, little x would be 5. So little x is the current toss, and capital X is when you're all done, how many successes did you get? So here are some examples. We have a coin toss, and we're doing it 20 times. It doesn't matter what the results are, we're going to do it 20 times. Previous tosses do not affect the current toss, so that's good. That meets our independent trial criteria. There are only 2 outcomes, heads or tails. Awesome. Probability of success is 0.5 in every time. So that is a great binomial experiment. The second one, 28% of Americans say that chocolate is their favorite flavor of ice cream. So we sample 10 Americans and ask, what is your favorite flavor of ice cream? Well, the experiment is done 10 times, so that's a fixed number of times, so we're good with that. And since it's a random sample of Americans, we can assume that they're not standing next to each other and influencing each other's answer. So those are independent trials. If we had not had a random sample, but maybe surveyed a family where, what some other people said in their family made them change their mind about what their favorite flavor is, then those trials wouldn't be independent and this wouldn't be binomial. There are only 2 outcomes. Chocolate is the favorite or chocolate is not the favorite. Notice this. If you ask the person what is your favorite, and one person says vanilla and the other one says strawberry, those outcomes have to be changed to chocolate is not their favorite. Because we can't have chocolate, strawberry, and vanilla and whatever other flavors there are. We can only have chocolate or not chocolate. So that's how that one becomes binomial, by the way we process the answers. And the probability of chocolate being the favorite is 0.28 in every trial, so that one works for a binomial distribution. The third one, 3 aces are drawn from a deck without replacement, and the number of aces is recorded. The experiment is done 3 times, so that's good. That's a fixed number. But in this case, the previous draws do affect the current draw because the number of cards in the deck has changed. So the trials are not independent, and we cannot use the binomial math on this one. Why? We start out with 52 cards. The first draw is done. That card is not replaced. So the second one is out of 51 cards. So they're not the same. The probabilities have changed. And those previous draws do affect the next draw. So doesn't work for binomial. So we're going to go over to this Excel right now to learn about how the formula binom.dist works. So here we are. And what you want to do here, this one's a little more complicated than what we have done previously. Okay, if you go up here to the top and find formulas, and then you look for statistical, and it's under more functions on my screen, but it could be somewhere else on yours. And we're looking for binom.dist, so binomial distribution. And you click on that, and it will bring you a more detailed explanation of how to use it. We have 4 parameters that we're going to be using for this function. And so let's look at this one. All right, so this time we are going back to this. If you toss a coin 10 times, what is the probability of getting exactly 3 heads and 7 tails? So we're going to fill out these parameters, and you can see that filled out version up here in this formula bar. So we're going to start with the first thing. The first parameter is this number underscore s. And what that means is the number of successes you are trying to get. In this case, it's 3. And then the second one is the number of trials. So we are tossing the coin 10 times, so that's going to be 10. The probability of getting success on every toss is 0.5. And we're setting cumulative to false because we want the probability of getting exactly 3 heads. All right, so if you look up here how we filled out with these numbers, that's the 3 for heads, number of successes, number of trials, probability on each toss, and false. And so when it calculates that, it found that we had 0.117 and so on, which if we round that to the nearest percent, that means there's a 12% probability of getting exactly 3 heads and 7 tails. We don't have to worry about the 7 tails because it's binomial. You know that whatever is not a success is a failure. So you can always just fill in that 7 tails. Because whatever is not a success is a failure. Whatever is not a head has to be a tail. So we have 3 heads, 7 tails. All right, here's another example. If 41% of people like to take walks around their neighborhood, and I made that number up, so don't quote it, in a sample of 20 people, what is the probability that exactly 5 like to take walks? Okay, so we're going to go over here. We're going to fill this out again. The success is 5 people taking walks. We're surveying 20 people. The probability for each person is 0.41. And we're setting cumulative to false because we're looking at exactly 5 people. And it turns out to be 6.5%. Right? And next we're going to try fewer than 6 like to take walks. So fewer than 6, we're going to set that cumulative to true now because that's going to change how this is calculated. When you set it to true, it calculates everything up to and including the number you put here. So in this case, it's finding the probability of 0 people liking to take walks, 1 person liking to take walks, 2 people, 3 people, 4 people, and 5 people, and it's adding all those together. That's what the cumulative does. When cumulative is false, it will just do the one number. When it's true, it will do everything leading up to that as well. All right. So in this case, we went from 6.5% to 10.8%. And that makes sense because we have more people that we added in, right? And at least 6 like to take walks. Well, at least 6 is the opposite of fewer than 6. So we can just do one of those 1 minus the fewer than, and get our number there because it has to be everybody else. Right? And this is the trickiest one, is the number of walkers is between 5 and 7 inclusive. So we're going to do 7 or less minus 4 or less, and that's going to give us 5, 6, and 7. So remember that when you set cumulative to true, it includes the endpoint. So by putting the 7 here, we're getting 0, 1, 2, 3, 4, 5, 6, 7. But then we're subtracting off 0, 1, 2, 3, 4. And that gives us 5 through 7 is what's left. All right, so we are done looking at the spreadsheet. Let's go back to the Word document and see what else is going on. All right, so here's a you try it problem that you can do yourselves. Suppose students are on time 80% of the time when it's snowing. I made up that number too. 15 students are randomly chosen and the number of on-time students is recorded. So first off, you're going to go through these criteria in part 1 up here and see, do they fit this situation? And in this case, we're on time. Early is on time, right? You will be there on time if you're early, so that counts as on time. And then you're going to find these probabilities, and the answers are here so you can check your work. All right, so that's it for binomial distributions. They're kind of fun to play with, and just take it step by step. Remember what's going on with the coin toss. I think the hardest thing with these is sometimes it gets confusing. Well, wait, if I'm looking for 3 out of 10, how can the probability be 5 out of 10? And you just have to realize that the probability is 5 out of 10, but things don't always happen the way the probability goes. So go back and remember that coin tossing situation where you're getting 3 heads and 7 tails. It is very possible to toss a coin 10 times and get 3 heads and 7 tails, even though the probability is 0.5 for each toss. It doesn't always turn out the way the probability says, and that's what we're measuring here. All right, thank you, and thanks for your hard work.